Now that we have an idea what sequences and series are, let's talk about writing them down. One way to think about a sequence is as a function whose domain is whole numbers. For example, let's take the sequence that looks like 1, 1/2, 1/3, 1/4, etc. I can think of this as a function where my input is which ordinal this is. So f of 1 is the first, f of 2 is the second, f of 3, second, f of 3 is the third, and so on. And because there's no in-betweens, it just goes from 1 and then 1/2, I define my domain to only be whole numbers. So for example, f of 1/2 doesn't exist, and f of -1 doesn't exist. For convenience, we often write a sub 1 for the first term, a sub 2 for the second term, and so on. So if I'm using the same sequence that I had before, think to yourself just for a second, what is A3? A3 is the third term, 1, 2, 3, so A3 is another name for 1/3. Sometimes sequences can have rules. Sometimes they don't. Sometimes it's just a list of number. A sequence doesn't have to have a rule, but usually they're interesting to us when they either have a rule or they come from real-life data. If I wanted to make a rule, I can say, well, in general, what is the nth term of the sequence? Well, the first term is 1/1, and the second term is 1/2, and the third term is 1/3, so the nth term is going to be 1 divided by n. We use some notation that can sometimes look a bit busy. This notation is describing this sequence. Let's dig into what all these pieces mean. These are our indices. So this tells us our first term is when n equals 1. Usually our first term is n equals 1, but not always. For example, we might want to start at years. So maybe our first term would be 2020. We don't have an upper bound. The sequence just keeps going without ending, and so we write infinity up top. And this tells us our rule. So our rule is that the nth term is 1/n. So again, the a sub 3 is 1/3. That's the third term, and so on. Now, oftentimes, because this is a lot to write, we don't write the whole thing. What you saw on the last slide was just a sub n is equal to 1/n, and this is how you'll normally see it. These bounds usually start at 1, or if there's some compelling reason, they'll start somewhere else. For example, again, they might start at a year. Consider a sequence that doesn't start at 1. Let's say every year we find the average cost per kilobyte of a consumer hard drive. So hard drives are getting more powerful and less expensive. So I expect this to be decreasing. So in 1981, 1 kilobyte of a hard drive would cost you $300,000. By 1984, that had dropped to $37,500, and now it's practically nothing. I want to show you two ways of describing this list. One way is recursive. Recursive means it depends on the previous terms. If you notice, 150,000 is half of 300,000, and 75,000 is half of 150, and so on. So I can write this recursively by saying a sub 1981 is 300,000, and a sub n plus 1 is 1/2 a sub n. Let's think about how to use this recursive function. If I wanted to know what happened in 1982, that's a sub 1981 plus 1. So that's 1/2 a sub 1981. I've just plugged in n as 1981 to this recursive definition. If I want to know what happened in 1985, 1984, that's 1/2 A of 1983, but I don't know A of 1983 yet. A of 1983 is 1/2 A of 1982. So this is 1/4 of A of 1982, which itself is 1/2 of 300,000. Recursive definitions are often easy to come up with when you're trying to model behavior. When you're trying to model behavior, it's often somewhat natural to say, well, if I know what happened in the last step, I can figure out what happened in the next step. But as we saw, they can be a little bit hard to work with because you have to one by one determine all of your terms, and you can't just skip to saying, well, what's A 2020 going to be? The counterpart to a recursive definition is an explicit definition. In an explicit definition, you can just plug in n and immediately get your term. This is an example of an explicit definition. Now, if I want to know what the cost is going to be in 2020, I don't have to find 2019 and 2018 and so on. I can just plug in n is equal to 2020. 300,000 divided by 2 to the power 2020 minus 1981. Why don't you pause the video for a second and practice using both of these definitions? $1982 was 1/2 of 1981. That's 150,000. 1983 was 1/2 of that. That's 75,000. 1984 is 1/2 of that. That's 37,500. Term 1985 is 1/2 of that. And term 1986 is 1/2 of that. Using the explicit definition to find A 2010, this is the same sequence. If you had continued with the recursive definition, you'd get the same thing, which will work out to 300,000 divided by 2 to the power 2010 minus 1981, which is 300,000 divided by 2 to the power 29. Let's practice some pattern recognition. For each of these, you should be able to find an explicit formula for the sequence. Take a minute, pause the video, and find these formulas. For my sequence A, the denominators are power of 2. Notice this starts at 0. 1 is 1 over 2 to the 0. So A sub n is 1 over 2 to the n. Now let's look at sequence B. I started n equals 1, so this is the n equals 1 term. My denominators are going up by 1. So when n equals 1, I'm at 4. When n equals 2, I'm at 5. When n equals 3, I'm at 6, and so on. But I'm just offset by 3. So the denominators look like n plus 3. The numerators have alternating signs, and the way we handle that is we take -1. If I take -1 to the n, -1 to the 1 is -1, -1 to the 2 is 1, -1 to the 3 is -1. I'm off by a negative, so I just add in an extra negative. This is a way to express Bn. You can also write it like this, -1 to the n plus 1 divided by n plus 3. Sequence C is very similar to sequence A, just offset. So instead of 1, we have 2. Instead of 2, we have 3. Instead of 4, we have 5. Instead of 16, we have 17, and so on. So my denominators are just 1 bigger than A sub n. So this looks like 1 over 2 to the n plus 1.